pointer. Okay, so thank you. Thank you to the organizers. Also, thank you to all the speakers and Claudia for that really nice talk. So I appreciate the opportunity to tell you a little bit about Cmb-Hd. So everything that I'm going to say is based on these white papers, and for more detailed references, look at the references within those white papers. So let's see. Okay. So I'm going to start with the science motivation for why we would want to build Cmb-Hd. So the primary science motivation was really dark matter. And the idea of one primary motivation of Cmb-Hd is something that's been called by other people extreme CMB lensing. So I like the term. But the idea is basically to make a map of dark matter in the universe. So Cmb-Hd will survey half the sky and make this map of dark matter on small scales. So in terms of multiples, you may be familiar with this CMB lensing power spectrum, but what may be new to you is that these multiples are an order of magnitude larger than you're used to. So you might think of multiples of 3,000, we're talking about 30,000. And so this will probe scales of K to like 7 inverse megaparsec. And the goal of that is to probe, the key targets are to make a map of the projected dark matter on small scales, measure the matter power spectrum, albeit the projected matter power spectrum on small scales over half the sky, and then also to probe different dark matter models and baryonic physics. So we don't want to shy away from scary baryonic physics. We actually want to measure the matter power spectrum so sensitively and measure its shape so that we can tell the difference between dark matter models that are alternate to cold dark matter and also different models of baryonic physics that alter the shape of the lensing power spectrum differently. And just as this was dubbed extreme CMB lensing, I want to mention one more point is that the advantage of using the CMB for gravitational lensing as opposed to optical lensing tracers is that the CMB is really well known. So it's just perfect for this. You know the redshift of the backlight. The primordial CMB on these small scales is basically just a gradient, and it's behind every object. So there are a lot of advantages to using the CMB as a backlight to do weak gravitational lensing. And when you probe the matter power spectrum with gravitational lensing, there are no complications of using baryons to trace where the dark matter is. And then more recently, what you can do with extreme KSC measurements, so we'll measure the KSC out to multiples of 40,000 or so, has been developed. So you can probe fractional components of dark matter, such as with some ultralight scalar. More recently, there has been papers on probing the polarized kinetic SC effect. So, so there are a lot of things you can do with high resolution kinetic SC observations. And this science is all unique to Cmb-Hd because of its resolution, which is 6 times higher than any precursor CMB experiment. So it can't be done by anything, even CMB-S4. Another science motivation, and so you can see my theme is a lot of fundamental physics, is to probe whether there are any new particles that we don't know about that were in thermal equilibrium with any of the standard model particles at any time in the early universe. So that's what this plot is showing. This plot is N effective, the number of light relativistic species. And what these colored curves are showing you the minimum change expected to the standard model and effective from any new light particles that were in thermal equilibrium with standard model particles. But the fact that Cmb-Hd can probe all the way down here, this red curve, and we show the comparison to CMB-S4, means this. So this is temperature of the universe. So this means we can probe the existence of any new light particles all the way back to basically the Big Bang. And that's important for many reasons in its own right. And it's also important for dark matter because many models of dark matter predict the existence of new light thermal particles in addition. So this would also rule out or potentially detect the existence of new light particles. Another main science motivation is inflation. And we heard a really nice BICEP talk earlier. Cmb-Hd aims to target inflation in a different way. So one of the main key targets is probing inflationary magnetic fields. And this is relatively new. But the idea is that the magnetic fields that we observe in galaxies today, are about micro-Gauss strength. And the question is, where did these magnetic fields come from? And if they came from nano-Gauss magnetic fields on megaparsec scales that were then just amplified due to the process of structure formation, that could be one explanation. And that's a compelling explanation. But in order for that to be true, then we need inflationary magnetic fields that are about 0.1 nanogauss at just after recombination. Otherwise, they wouldn't generate the magnetic fields we observe today. So with the Cmb-Hd target, we would be able to detect inflationary magnetic fields at about the 3 sigma level or higher, depending on where they are. And this would be a smoking gun signature of inflation because no other effect could generate scale invariant primordial magnetic fields of such large amplitude. So it would be a smoking gun signature of inflation. And the way Cmb-Hd achieves this constraint is through its measurement of anisotropic birefringence, so through polarization. But what's neat about the signal is that it has this very specific frequency dependence, the new to the fourth dependence, so you can separate it from any other signature of anisotropic birefringence. So that's neat. Another target, also probing inflation, is local non-Gaussianity. So with the combination of the high resolution kinetic SC effect from Cmb-Hd plus the galaxy survey from the Vera Rubin Observatory, Cmb-Hd can probe local FNL of about 0.26. So you see the Planck level here. And that could allow us to detect or exclude this key target of FNL local of 1 at about 4 sigma. But another point to make with this is that this is limited by the galaxy survey of the Vera Rubin Observatory. So future large-scale structure surveys could allow us to probe, get this constraint even lower. And then what wasn't a science driver, but is really neat that you can do in addition, is probe dark energy. So this was work by this team here. So you could probe dark energy to the sub% level and as well as the neutrino mass. And this constraint on the neutrino mass is only assuming the current Planck tau prior, so nothing better. Of course, if you had a better tau prior from, say, Lightbird, that constraint would get even tighter. And this constraint is, this particular constraint is from using TSZ clusters plus CMB gravitational lensing to measure the masses of clusters, but it doesn't fold in the additional constraint you have from CMB lensing, straight CMB lensing power spectrum. So that's a lot of fundamental physics. I wanted to mention that there's a lot of fun astrophysics with such a survey. And then I'll describe the specs of the survey. So for planetary studies, there's an advantage to using millimeter wave observations over optical. And the problem with optical is that you see planets, like door-sized planets, you'll see because of sunlight reflected off of them. And because the optical light falls faster than the millimeter wave emission that's intrinsic to the planet itself. If you want to see objects far away, you actually want to look in the millimeter. So an instrument like Cmb-Hd would allow you to detect dwarf-sized planets hundreds of AU from the sun, or even Earth-sized planets thousands of AU from the sun. So say if there's a planet 9 out there, for example, you'd be able to detect it just using the intrinsic millimeter wave emission from the planet itself. And then you could also, we don't know for sure if there's an Oort cloud around our solar system. We could look around other stars and see if they've got some exo-Oort cloud by looking at the millimeter wave emission. Then, of course, for the folks interested in the SC effect, we would, and because of the high resolution, we would probe gas physics out to halos of z=2 and with masses down to 10 to the 12 solar masses. So to really understand the evolution of the gas physics. And then in terms of the transient science, we calculated the flux levels we would achieve. So there would be a daily 8 sigma flux level of 4 millijanskis. And the goal of Cmb-Hd is to release weekly maps with a reference map subtracted for people interested in transient science. And we would also have a catalog of galaxies, AGN and dusty star forming galaxies with a flux limit above 0.5 millijansky at 150 gigahertz. And this is a 10 sigma survey limit. So now that I discussed all of that science, what's needed to achieve that? So we really need a sky area of 50% of the sky to average down sample variance. And the noise level has to be about 0.5 micro K arc minute in temperature. And this is in your combined CMB channel, so 90 plus 150 gigahertz. The resolution needs to be 15 arc seconds, not only to achieve the high resolution, say for the CMB lensing power spectrum, but also to remove foregrounds enough so that you can realize this low noise level. Otherwise, the foregrounds will just contaminate everything. And then because we're talking about a big dish, obviously, because we have high resolution, the minimum multiple that we need for every single science case I mentioned, except for the inflationary magnetic fields, is only 1,000. And so that's good because it is hard to achieve low multiples with a big dish. And so if this science is not able to be achieved, then so be it. But if you can achieve BB measurements down to L of 100, then you can achieve that science as well. The reason why I only mentioned BB is because Simon's Observatory will already be measuring multiples of 30 to 1,000 to the sample variance limit over half the sky. So they'll measure TT, TE, and EE to the sample variance limit. And so we don't need to reimage those modes, but that won't be the case for BB. And then frequencies to foreground clean, there'll be 7 frequencies. And the white paper summarizes all of this succinctly, so you can look there if you are interested in any forecasting. So the instrumentation that would be required to achieve those specs are 2 telescopes, 2 new 30-meter class off-axis cross-dragone telescopes, a detector count to achieve those low noise levels of 800,000 per telescope. But each pixel is 4 detectors, so 2 colors and 2 polarizations. So it's 200,000 pixels per telescope. So very large number of total detectors. And then the site would need to be in the Atacama Desert as opposed to, say, the South Pole, because we need 50% of the sky. The duration to achieve those noise levels is 7.5 years. So the timeline, so this is a plot from the recent SNOMAS 2021 CMB measurements white paper, which was signed by a large fraction of the CMB community, is to have detectors on sky by 2034, which is pretty ambitious. And for details, I invite you to look at a whole number of white papers. There's also up-to-date information on the website. To date, the collaboration has about 60 scientists, mostly CMB experts, and it's quite open. There are no barriers to join. Just let me know if you're interested, and there are no commitments of workload or anything like that. Now, the data analysis challenges, which I'm very happy to share with you because they are significant, and I welcome all your brain power to think of creative ways that they can be surmounted. So we're talking about huge data rates, much larger than precursor CMB surveys. So the estimate of the instant uncompressed data rate is about 2.24 gigabytes per second. So that would yield 190 terabytes per day, or 67 petabytes per year. And you could reduce this by a factor of few with compression, but that's about it. So with 7.5 years, you'll have about 500 petabytes of data. And while storing this much data is very expensive today, hopefully in a decade, it will be much more feasible. So there's a lot of data, but okay, so challenge number one. Challenge number two is the maps and the simulation. So the resolution is 6 times higher than current high resolution ground-based instruments. So we're talking about 15 arc seconds versus more standard 1.5 arc minutes at 150 gigahertz. And the maps are 50% of the sky. So if we use the HELPIX maps that we all know and love for 8192 that have a resolution of half arc minute, they're about 3.2 gigabytes for a full sky, double precision. Making car maps with the same resolution, single precision, is about 3.6 gigabytes. So we will need full sky maps, probably with 5 arc second resolution, so that we can be slightly oversampled, and they're gonna take up more space. So that becomes a challenge, not just to store them, but also memory limitations, like what maps you can load, how many you can load at the same time to process, etc. And for covariance matrices, you would envision at least hundreds of simulations for covariance matrices and bias subtraction, etc. And I was at a talk, I was giving a talk last week, or actually just in a discussion section, and the issue was brought up that LSST is using something called cloud computing, which I hadn't heard of, but I thought this was a neat idea of, instead of downloading the data, so instead of everybody downloading the data and working on it, what about centers to upload your software and have the analysis done at some site where the data is? So I think LSST is already implementing this. Sounds like something we would need as well. Another challenge, more immediate challenge for forecasting, is just the high L's that we're talking about. So at a minimum, to forecast, so for Cmb-Hd, so my group is forecasting parameter constraints, etc., is that you want to go out to a multiple of 20,000 with your CMB power spectra and CMB lensing spectra at a minimum. So we've been playing around a lot with all of the default settings currently in CAM and class. You definitely need to use high accuracy settings, which do take longer to process. My grad student using a proposed matrix from her Fisher analysis can get convergence in about 3 days using Monty Python. She's trying Cobaya next. But work on this is in progress. It does seem tractable, and we should be putting out likelihoods for HD soon, hopefully even integrating it within Monty Python and some of the other codes so that people can forecast whatever they would like to forecast. And then the final, probably most challenging part of Cmb-Hd is the foreground cleaning. So where we would like to be is this plot over here, where most of the foregrounds within this range of say 5,000 to 25,000 are below the noise. So this, I'm just showing the 150 gigahertz channel. So we will have 7 frequency channels and high resolution. And what that high resolution gains you is the ability to find sources down to much lower flux limits and template subtract them, meaning know the shape of the beam, measure their flux, and subtract them from the map, not cut holes in the map so that you have Swiss cheese. And that'll, at least for CIB and radio, you know, they'll follow largely the shape of the beam. It'll be a little bit more of a challenge for TSC, but we will have a higher resolution. So my group's in the process of demonstrating a lot of this with simulations. We did do a first step. When I say it's just a first step, where we said in principle, could we deal with the worst foregrounds, which is CMB and TSC, and get the biases to the lensing, CMB lensing signal under control, which seemed promising. Some work that needs more work is removing the frequency independent late time KSC. So you'll notice I don't have that on this plot here. There are a number of groups that had been exploring it. I just heard a talk 2 weeks ago by Kendrick Smith, who was talking about using the KSC 4-point function and saying that that would work well to remove the late time KSC, to separate the late time KSC and the reionization KSC, because they have a different 4-point function shape. So I think there's a lot of promising ways that foregrounds can be dealt with. I think there's lots of room for new ideas, and the whole KSC field also seems kind of in its infancy. And then probably, if you ask me, I think the CIB will be the most challenging to remove cleanly, but these sub-millimeter instruments like CCAP prime, probably at last as well, can help let us know if we've cleaned the CIB effectively. So to summarize, Cmb-Hd will be a big leap beyond precursor ground-based experiments in terms of the resolution and the noise. So to give you a sense, it's 6 times higher resolution than precursor high resolution surveys, and also 3 times lower in noise than the CMB-S4 planned wide survey. There's a lot of compelling fundamental physics targets that one can reach. So really targets where you'll learn something fundamental, even if you have a non-detection, as well as astrophysics. And for this group, there are significant data analysis challenges. Hopefully that will stimulate a lot of not new directions, but there's super high data volumes, questions of where to store it, how to analyze it, the need for simulations that will take a lot of space and time to process. We are definitely pushing the regime of our likelihood codes and what the current codes are capable of doing quickly. And there are a bunch of foreground cleaning challenges, and we definitely welcome any and all novel ideas, or just go and write papers about the novel ideas you have. It'd be greatly appreciated. Okay, thank you.